today is going to be one of those 4 lectures on alternative models. So it's the first lecture, and I'm going to bring your attention to this very interesting model called, it's pronounced RWKV, the full form being Receptance Weighted Key Value, right? And we will show throughout this discussion how this model differs from the traditional transformer-based models, including the modern LLMs that are based on transformer-based decoders. All right, so this is the paper. The paper was published in findings at EMNLP in 2023, but after that it got a lot of traction, and subsequent many other RWKV-based models were published in top tier venues. So I thought that this is something that we should start in terms of our discussion. And why this is interesting is because it's sort of like a bridge model between the RNN styled architectural models and the later on transformer styled architectural models. So because it's a bridge, let me just give you some very quick recap over what all went through over time in terms of modeling language, like chronological advancements, right? So if you look at the statistical language modeling, you'll see that as an example, if you have a sentence like John loves Mary who lives in New York City, the usual the language modeling problem is that you have to predict what is the next token given a sequence of prior tokens. So it is always an estimation of the conditional probability density once you, in an autoregressive setup, once you have new and new tokens predicted within that autoregressive setup, right? So as an example, in this particular sequence, you see that there's Mary is both an object of loves, right? John being the subject, and also a subject of lives in. So it's an object of loves as well as a subject of lives in, right? So essentially it has two different grammatical aspects, So we will carry on with this particular example all through to help you understand this particular model and how it differs from, or the contrast with existing models. So a standard, classical way of representing this conditional probability estimation, density estimation, is to approximate this as an n-order Markov chain, which we know in NLP, we know it with the more popular n-gram language modeling, right? And the approximation is this, that you don't have to go till the very beginning of the sequence. You can just go backwards till n steps, and that is good enough to carry the entire sequence's information content. So what Markov would mean is that you don't really have to go to the entire ancestry of your lineup. Just to give you an analogy, you can just look at your grandfather, and your grandfather will have all the information of your great forefathers. So that's the Markov assumption, basically. So if you go till your n steps before the particular token, then that would be an order, right? So that's the first thing. The limitation being that, well, it's fixed window. There's no explicit structure modeling in terms of how one token specifically influences the other token and so on, right? It's almost like a a snowball principle where you keep accumulating the snowball across time, and all you're doing is that how the snowball collectively, cumulatively influences the next token. So it doesn't have a very intrinsic understanding of what each part of that snowball, how each part of that snowball is actually influencing, right? Another way of looking at it, in a more advanced way of looking at it, is that you model it as a HMM, but HMM in this case is modeled more as a language model, and you have this latent variable called Z, and this latent variable, which is basically the unobserved variable, that gives you an emission in terms of what you can see, which is X. And from there, you can actually come with this particular way of approximating language models. So you can say that, okay, what is that conditional probability of the next token given a sequence? A prior sequence is basically a sum over all possible latent variables that is connected to that particular token with respect to all the other tokens that is preceding that particular latent variable, right? And you sum that up. So that's another assumption, which is the hidden Markov model way of doing language model. Then what came up is that more explicit way of figuring out how the different parts and pieces of that cumulative memory or snowball, so to say, affects the next token, right? So and then we came across the era of LSTM, where we introduced that, okay, we would introduce so basically it's a gated RNN, and where we have different types of gates. So we said that we will have one kind of gate called the forget gate. And what would the forget gate do? It will try to figure out that if there is noise that is coming in as a part of the memory, I'm going to eliminate that noise. Or if there is something that is irrelevant that is coming in as a part of that memory or the history, I'm going to eliminate that redundant history, part of the history, right? And then whatever comes in, I'm going to take that, and I'm going to create a resultant of that with the incoming input. Again, the incoming input, I do a gating on top of that, which is the input gate or the update gate. Sometimes it's also called the update gate. And what we are doing over there, we're saying that, okay, so we do not want the input to overemphasize a particular aspect of the memory that is already there, present in the memory. So don't try to re-emphasize something that is already present in the incoming memory of that cell. So that's why you have an input gate, which basically takes care of some sort of redundancy, if at all there could be a redundancy. And then we have whatever it flows on to the next cell. So we have, again, we put a gate on top of that, and that would be the output gate. And my way of interpreting that is, one reason could be that you might again come up with reintroducing the noise that you just tried to eliminate or minimize via the forget gate. But that may be again reintroduced within the input. And why noise? It could be something that disturbs some downstream task. That could be classification or regression, or it could be something that is irrelevant, that is not relevant as of to the next subsequence. Okay, so this is a familiar, I hope that this is a familiar set of equations. I'm not going to go into the details of that, but this is extremely important to keep in mind, because Rakov took a lot of inspiration from LSTM. By the way, just a small little digression. The S is in red and italics because it's still short, although it can capture a good amount of longer dependency, but it still fails to capture very long context, right? So at the end of the day, it's not a long term memory, but it's a long short term memory. So that has to be always understood about LSTMs, right? So basically the gate learns what to retain or overwrite, and it leads to a learned Markov drift, right? So the Markovian drift in LSTM is, if we look at it with this example, so let's say that at the word who, the hidden state still carries Mary through the clause. If ft, which is the forget gate at that time step, decides to keep that information, and it should, ideally it should, because Mary is important for who, because we need to know that who is actually Mary. So the information of Mary should come in and not be eliminated by the forget get. So that is an important thing to understand. The limitation again being that sequential dependency, it's a very implicit retrieval. It's not very explicit in the sense that explicitly trying to bring the influence of Mary and the influence of love and the influence of John onto who, let's say, as an example. So you are not explicitly trying to pick each and every single preceding token and trying to understand what percentage of influence that has on who, right? So it's in that sense it's implicit, right? And again, as I said, like it's still short at the end of the day. So very long range, you will see that many of that effect goes away, and it's still Markovian in a sense, because it's in general it's always going to give more preference to tokens that are in the near past as to tokens that are in the further past. Now, if you look at from there onwards what happened in transformers, or rather in the self-attention part of the transformers, you can think of it more like a generalization of a scriptgram language model. So from n-gram language model to gated n-gram language model. So now we are in a generalized version of scriptgram language model, right? And what we do over there is that we have these three components: query and key and value, Q and K and V, where Q is the target word or the word that you have to contextualize in terms of embedding. It has its two other avatars. One is the key and one is the value. So we can look at it from this point of view that when it has the V avatar, then it acts like an influencer. So which means it influences other words in the sequence. When it has the Q avatar, it acts like the token which is getting influenced, right? And K is almost like a representative of V or a secretary of V, you can think of it like that, where K is the guy who does the handshaking with other Qs, in terms of figuring out whether there at all can be a handshaking or a friendship or some sort of an influence or association, basically, that can happen with that particular word, right? And the one way of looking at it is that now when you try to figure out the final ZT, which is the contextual embedding, well, all that you're doing is you're trying to take certain percentage of the neighboring VIs and adding them up, including its own VI, and adding them up, where that percentage is omega over here, omega Ti, where omega is basically that softmax that you do. So it's basically the softmax of the dot product between Qt and all the other neighbors, but this time you are doing the handshaking. The dot product is the handshaking over here. So you're doing the dot product or the handshaking with the neighboring keys, right? So that's the thing. So for this example, who attends to Mary as an example explicitly, while city explicitly, separately, independently, is being influenced by new and York and in and lives and so on. It actually gets influenced by everybody, by the way. I'm just giving you a small subset of that thing, and it aggregates all of those influences in terms of new and York and in and lives, right? So it aggregates over the V of new, the V of York, the V of in, and the V of lives, and that all comes in. And of course, it also aggregates John and loves, and Mary, and who, and so on. So why is generalized? Yeah, by the way, but in a standard, typical, classical transformer sense, it will take a quadratic time because everybody is handshaking with everyone else, right? So if you look at it like that, everybody is trying to handshake with everybody. So as a bipartite graph, you can think of all the Q's on one side and all the K's on the other side, and everybody has a K, corresponding K. So that's how it's T square, or in terms of where T, capital T, is the length of the sequence. And also during inferencing, it's heavy on the KV cache, and I don't know whether you have already studied that, but if you think about it, you'll see why that is so. So RWKV comes as a bridging between the RNN era models and the transformer era models, right? So what's the goal? The goal is that, the idea, the inspiration was, or the motivation was, can we somehow get the good thing about transformers, which is the high quality attention, the self attention, can we bring that in? But at the same time, can we also bring the more Markovian aspect of RNNs? Because what happens in transformers is that you are adding another additional assumption over the Markovian assumption, saying that it's not only n order Markovian, but it is also conditionally independent, right? So that if you look at the skip-gram model, what it says is that it's not only n order Markovian, but you are again splitting that probability condition into factors. You're factorizing it out, and you're saying that no, it's conditionally independent also, right? So you don't really have to look at the entire sequence as a whole, which means you don't really have to do the snowballing or the cumulative aggregation of memory anymore. But what if we don't want to do that? We want to have the global content mixing of transformers, but at the same time, we also want to do something that RNNs did. However, RNNs were sequential, right? And all kinds of RNN architectures are sequential, which means you cannot process all the cells all together at the same time. One cell has to wait for the previous cells to get processed, and then only a particular cell at a particular time step can process. It's like a while loop, putting it into a for loop. So you can't really parallelize that. So the attempt, and it was quite a bold attempt, that can we parallelize this thing. So what they are trying to do is like, okay, the content at every state, every time step, they call it S in terms of the state of the cell. LSTM used to call that content, or C. It's just a notational difference, but the same thing. So what they say is that, okay, can we have some sort of the same percentage of the VIs, where V is the value, the same percentage concept, we just keep adding the different percentages of how every single VI is influencing the Q, but instead of the softmax and the dot product kind of percentage, we do it in a different way. We try to do it in a way which mimics or which models the Markovian drift. So if you look at the factor beta I alpha, and we are going to make it very explicit what each of that means, but if you look at that equation itself, forget about what beta and alpha means for now, but if you just look at the numerator and the denominator, it's very clear that it's basically some sort of a percentage that's happening basically, right? So you are essentially, the numerator is one specific neighboring token, which is I, and the denominator is you are actually comparing that across all other j's, including that I, right? Okay, so just for now, you just need to understand that beta is basically the content strength, which is how much Vi is going to influence a query, let's say, and alpha is that exponential decay over time across the entire whatever happened before that, right? So basically, and that alpha is what brings that Markovian drift assumption back into the play, right? So we'll don't worry about this. We'll look at it in more details. So this is the architecture in general. It's also a stacked architecture. For now, just remember that it's a stacked architecture, just like transformer, with the final layer being a head, which actually does some downstream task. For auto regression language model, it will just predict the next token. So that's the final head. So that is pretty much the same. So we will go one by one. So let's first look at the first the Rokov encoder first. I mean, the decoder is the head basically. Let's look at the encoder. So the first step is the time mixing step. So what it does is that it says that, okay, so we have let's look at the word that is coming in right now. Let's say John loves Mary. So let's look at Mary right now, and let's say that xt is Mary, right? And so which means xt minus 1 will be loves. So let's look at these two words only, just bigram, very simple, bigram. And let's try to see to what would be the percentage of Mary that I should bring in, and what should be the percentage of loves that I should bring in. So this mix k, I have changed the variable name a bit. In the original paper you will see that as mu, but I like this more because it tells you what it actually is trying to do. It's basically trying to mix up these two words, Mary and love, let's say, or between John and love, love and John. So that's what it's trying to do. It's trying to mix the content, the information content of these two words, right? So it says that if with certain percentage I will take Mary, then 1 minus that percentage or 100 minus that percentage I will take love, right? And I will create this new mixed version of information at that time step, which means what is the situation till now, which means till Mary. So John loves Mary has occurred, and I'm focusing on Mary right now, which is the third word, and I'm trying to understand what is the situation till Mary, and that is xtk, right? Now what I do, I say that, okay, I do the same thing not only for the query, I do the same thing rather for the key, I do the same thing for the value as well. So I do a very separate mixing for the value, and I do a very separate mixing for the key. Remember, the key is the representative of the value that in transformer used to go and do the handshaking with the query, right? Now there is no handshaking in RWKV. In RWKV, no handshaking happens, so there is no queue, so to say. It's just we have the key and we have the value, right? So we do a mixed representation in terms of bigram of these two. And then we have this third thing called receptance, and we'll come to that later, but we just for now just know that there is something called a third entity or a third avatar called receptance, and we will later on see why we need that, which is the R. Now, one important thing to understand over here, although it looks like sequential, right, which means I first have to process xt minus 1 and then I have to process xt, but you have to understand that xt and xt minus 1, if you look at it, look from how we give input to a transformer. So we give input to a transformer like a matrix, like a whole X, capital X matrix, right? So where we have all the sequence as a matrix given as a whole to the model. That exact same thing happens over here. So essentially, when you are giving xt, you also have access to xt minus 1 at the same time, during that time only. This is not a snowball. Xt minus 1, unlike RNNs, in RNN, this xt minus 1, instead of xt minus 1, you would have had something like ht minus 1 or ht, the history that is coming in, right? That is not what it is, because if that was so, then you would have had to process the history first. So you have complete access of all the x's as of now, right? So that's what makes this parallelized and linear time also. Okay, so yeah.
So there is no hidden state that is being passed, rather absolute tokens are being passed.
As of now, yeah, the hidden state will, there is something called the hidden state, but since the processing at every step is happening in one single shot, even the hidden steps, the intermediate steps are also happening in one single shot. You can parallelize it through the cores of your GPU. Essentially, that's what happens at the CUDA level.
But this will mainly consist of just like 2 gram.
Yeah, I'm coming to that. You feel like, it's almost like bigram, so it cannot be that. So I'm coming to that, and that's the beauty of this model. Okay, so as an example, let's say for Mary, I just said, right? So you mix up Mary and you mix up loves and you create a key for a mixed key, and similarly you will create a mixed value. And the local bigram blending is basically so we call it the technical term for looking it up, just by one index shifting. The technical term is called token shift. That's a fancy way of saying that you are basically, looking up the previous index and calling it up. Okay, and this idea of mixing the bigrams together, like the previous one and this one, that's called time mixing, because you are mixing two different time steps together. Okay, all right. Now somebody can ask, why not 3 gram? Yes, you can do that. That was not what they did, but you could have actually combined 3, but again that would have been linear time because you have access to everyone, right? So but that is not needed according to them for one interesting reason, and I'll come to that. Okay, before that, let's just look at why this receptance is needed, right? So this receptance, what it does is that it helps you to create. But we will come. Okay, let me first look at. Let me first give you something to do with the gates that we create on the key and the value, and then we look at what this receptance actually does. For now, let's just hold on to that there is something called receptance, and which will be important. So, so now the beta. We talked about, in that earlier slide, you saw the alpha and the beta. So as I promised you that I'm going to tell you what that is. So beta is basically a gate that is an exponentiation version of the key. It's an exponential version of the key only, right? So the key that you just created. And alpha is also a gate which acts like a forget gate. So while beta is like an update gate of your RNN styled models, alpha acts like a forget gate, right? And why that is a forget gate is because it is basically an exponentiation decay minus w, which means it's an exponential decay of a learnable w. So w is learnable, not a constant. And and you apply that alpha over all the prior steps, right? And how that is applied is this way. So basically, you have you do this. You apply alpha to the prior state. Let's say that let's call the prior state at minus 1. So let's say that is the prior state, and you apply alpha to that, which means you want to decay that. You want to decay the effect of that state, right? And then you apply beta to the v. Why? Because beta is the update gate. So the update gate is applied on what? On the actual value, because that is the percentage that you need to bring in, percentage of v, just similar to transformer, right? So the percentage is actually will come from the beta. I'll show you how. And then you have some bt, which is formulated like this, and this bt acts like the denominator in terms of how a particular time step is contrasted with every other time steps, prior time steps, right? So what we can do is we can write at, if you unfold it, then you can write at as a summation over alpha t minus I over all the prior i's, and you can then bring beta I, that sums over all the prior t minus I. So if you look at the first alpha being alpha raised to 0, right? So that is 1. So that will be beta t vt. That is the second term over here, that is this term. So this beta t vt can be written as alpha raised 0 beta t vt, and that's how you bring the alpha inside the summation, and you can sum it over all the prior time steps, right? So that's your at. And beta t bt can also be written in a similar fashion, but over there you don't have the v. Then what you do is you say that your final content st is a contrast of at, which is your actual real deal, over all the other ats. So if you look at bt, then bt is basically a summation of, and if you plug that summation, this second summation of bt, and if you bring it inside inside the summation of at, then this is how it will look like. And you can say that this particular term, which is beta I alpha t minus 1 divided by summation of all of such beta i's alpha t minus 1, all of such across all the steps before that particular step, gives you that percentage, right, for that particular vi. So what I did was, this is not how it is structured in the paper, but what I did was I'm doing this so that you can see this analogy between what really happened in transformers versus what actually is going on in RWKV. Everything remains the same, which is omega is still a simple x over 1 and omega t comma I is greater than 0, right? Okay. So while the omega of transformer or the attention score of transformer is an exponentiation of the handshake or the dot product of q and k, in Rakov, there is no handshaking between q and k. It's just that you write it as a multiplication of beta and alpha, where beta is e raised ki and alpha is the e raised minus w over t minus I, right? So that's the if you want me to pause here for a while, how what is the parallel and what it really means, you can think over a while maybe. And okay, so it's like a decayed co-occurrence weight, co-occurrence in the skip-gram sense, right? And nearby tokens contribute strongly. Distant one fades unless reinforced. Now, unless reinforced means what? Where xt, maybe xt again, a new xt comes in and again introduces that information back into that memory, right? So unless that happens, it's going to fade. When I read the paper, the original idea is how to make it linear time. And because you are no more dealing with history, the cumulative history, because that has to be processed, because that makes it sequential in RNN based models, right? Because you have to wait till the prior history is computed and then you have to add that with the incoming new input. Over here, yeah.
So RNN had that issue, right?
RNN styled models have that issue because at every time step you have to wait till the previous history is computed. Transformer, that's not that. So they took that idea from transformer. They said, okay, we are not going to talk in terms of history. We are going to talk in terms of the tokens that are accessible. But instead of what transformer did by looking at all other tokens in the sequence, what they are doing, okay, we just have to focus on 2 tokens at a time.
So here from linear, I believe means linear time attention calculation.
Yeah, linear time attention calculation. Yeah, so I mean, and that's what I'm saying. So linear means not in a absolute linear sense, I don't think, but n log n or something like that have happened, even by restricting the context window and trying to make it.
But this is the order of incident, right? What in terms of order? Because you're looking at 2 words at a time, 3 words at a time.
No, what, and so that's the thing. So what? Theoretically, yes, but in practice, where the parallelization happens is here, because when you are, it's not that you are trying to process xt minus 1 and then later on you are processing xt and then you're actually doing it all in one go, and there is no loop essentially, because you have access to every single xt, so you can do a multi-threading over at a CUDA level over on your GPU.
In that sense, if you consider that sense, then transformer attention is also linear. Because you can do all this computation in parallel. I'm talking about algorithmic complexity. I'm not talking about complexity in terms of GPU access or making it parallel.
No, even okay. So
So if you tell me, I mean, are you trying to improve upon RNN or you are trying to improve upon transformer? What's the base here?
So I think if you ask me my opinion about Rocco, I look at it more in terms of how you can bring in the idea of Markovian drift into something like a transformer. I'm less interested personally in the linear time attention pickup that they showed. I'm more interested in the hypothesis, the Markovian drift hypothesis. Is it better or equally as good as the plain and blatant independence, conditional independence skip-gram model that transformer has? Which means, see, if what I'm more interested in terms of the science behind it is, or the scientific question is, that the percentage that is coming in terms of skip-gram or transformer, let's say how much percentage John, in this example, with what percentage John influences Mary, right? Now skip-gram or transformer would be like, okay, let me learn it. Through data I will figure it out, right? So which means I will try to figure out actually to what extent the query of Mary can go together with the key of John, and that will determine what is the percentage, and I bring that percentage on to the value of John. What these guys have done is these guys are saying that no, you need to add an additional aspect of exponential decay, which is because if you do with the transformer, you are no more assuming the Markovian ness of it, because then even something which is quite away, far, can have higher percentage than something which is nearby.
How can that be a higher percentage? Because attention will figure out that if something is very far from T, your current position, the influence will be less. The attention will automatically figure out. I'm not talking.
I mean, it depends upon what is the association.
Yeah, so I'm not talking about very simple query dot plot. You can also think of a linear progression. Let's say query W into you have a linear layer between query and key, and so let's say I mean Q W K, something like that, and because there are multiple variations of attention, right?
Yeah, see, like the associations in attention can be all kinds of syntactic associations and all kinds of semantic associations, or lexical associations, right? And that is why you need all the different types of heads, and you have layers so that you can capture longer dependencies also. So at different layers and different heads, you have different patterns of association that are getting captured, right? So, so as an example, if you want to look at from a pause tag association, that would be one kind of association. Those are nearby associations. But if you look at in terms of the dependency grammar kind of association, that's more longer associations, right? And that's why you have different heads. The entire concept of why multi-headed attention is needed comes from there. What these guys are saying, they don't have heads, by the way. So Rakov doesn't have heads. They have stacks, or they have layers, but they don't have heads, multiple heads. So what they're saying is that if you do that, what they're saying is exactly what you're trying to point out, which is if you do transformer, it is as good as doing a normal Markovian, learning. So you don't really have to, so which means what they're saying is that John cannot influence Mary more than loves. Or even if it does, it should get a punishment because it is far away from Mary in comparison to loves. So what it's trying to do is trying to balance this percentage with two norms, beta and alpha. So while beta does something which is sort of analogous to what transformer would have done, which is what is the natural percentage or the natural relationship association, what alpha does is that no, despite the fact that let's say that John has higher percentage with Mary association with respect to, let's say, loves, let's say John has 70% association and loves only has 10% association. If that is so, then Rakov is saying that no, you need to bring it down, that 70%. Because even though John is 70%, it has to decay. So that additional alpha in the numerator comes in terms, and that is a function of how further away you are from that particular time step. So that is the assumption. But now whether that assumption is, whether language actually works like that, that is, the results will show whether this hypothesis is valid, or to what extent this hypothesis is valid. But I think that was not the original motivation. I think the original motivation in 2023 was more in terms of how to reduce the time complexity and also the space complexity. I think that was the original motivation.
One of the main reason of improvement in LLMs is like the bigger context window.
Right.
But here, because of decaying, we are saying that no, we should not have long context window.
Yeah, okay, so theoretically this can have infinite amount of context, right? So the interesting thing about this model is, it can be anything. You are not putting a bar in terms of the context length as such, because anyways it will vanish away. It's like a tail. It's the decay will take care of that. So anyways, you can have as many number of context length theoretically, but yeah, but it will just remove the effect of very far away stuffs.
Yeah, exactly. So that means there is no point of having long context window.
Right, but we will look at some of the comparisons with the longer context models and how it performed on that, right? And we will see. This is something interesting on that as well. Okay, so the inherent Markovian drift over here is that with alpha, which is within the range of 0 and 1, older info decays exponentially, and the memory ST, or the state, drifts towards recent high beta tokens. So it's not also that there is no beta, because if there is no beta, then you are taking a very radical sort of a position, saying that no, it's always going to be purely Markovian. So which means that only the most close one will have the highest percentage. So you're not all doing that as well.
What are the learnable parameters here? Alpha, beta?
The learnable parameter beta is basically a function of your learnable parameters, right? So beta is exponentiation of kt. Kt itself is so the wk and wv, and I'll talk about the receptance, what it does later on. But this is the encoding part. Yeah,
Extra parameters.
the mix, because you are doing this xt is a mixed version, the mixed version of x.
No, but mix is a parameter or hyperparameter?
No, mix is the hyperparameter that you learnable. Okay, so at who, as an example, influence peaks at Mary, earlier John fades unless refreshed. So that's the idea. All right, so now comes the R part. So this was the WQV operation. So this is called the WQV operation. So the one in the red box. So that's actually the WKV operation. Now the R. So what does the R do? So it's called the receptance, and it's basically used to create yet another gate that has the analogy with the output gate of an LSTM, right? So we already saw the forget gate, which is the analogy of forget gate would be alpha. The analogy of update gate would be beta, and this is more of a analogically, this is what they have for output. But so it's basically a sigmoid of on this RT, which means bringing everything into like a percentage. Uh, and then you normalize, you layer normalize. The ln is layer normalization. So I'm in my equations, I've not shown all there are 4 or 5 layer normalizations that happen in the entire architecture. I'm just showing you this most important one over here. So you do a layer norm on the ST, and then you apply the gate on the ST. So what it means is that your final contextual embedding, which is YT in this case, right? The final contextual embedding, to what extent that should be born out of ST. So which means what percentage of ST should you use to create YT? Okay, so that's what receptance is all about, which means what percentage of ST should you receive, accept in order to create YT. Okay, so this is the R operation in that RWKV operation. This is the R, the underline, the red underline. That's where the R operation is happening. Okay, all right. So now comes the second kind of mixing. So what do you do before you start this, which we call as channel mixing? And the channel mixing can be thought of like an analogous version of what you do before you send in your transformer, before you send your information, the contextual embedding, to the next layer. You have an in-between FFN, a shallow FFN, feed-forward network. So this acts like that. It's like an analogous to, an alternative to the FFN that acts between the two layers. So you first do a residual so that the soul or the crux of the information is not lost. So you essentially add XT as a residual onto the newly formed YT. Where is YT? YT is over here. So you got the YT, you add the residual to YT, you create a YT prime, let's say, and then what you do, you mix YT prime at two different fronts, right? The first front, again, the same thing that you do, again in the bigram level, again parallelizable, because since everything is happening in parallel in one shot, you got the YT and the YT prime, YT minus 1 at the same time. And that's why you can do the mixing in parallel, right? And the first mixing is for something to do on applying yet another forget get, and the second mixing is an update, yet another update gate, right? So you get two different versions of Y prime T. I just named it XT, but I should have named it YTF and YTG, but it's okay, fine. So this XT, then you create the final update or the final state using this WF. That's a linear transformation on the XT basically. So think of it like what happens in that FFN. So there are one hidden layer, right? So you do one single linear transformation, expand it in terms of the dimension. Again, you do another linear transformation, contract it, and then send it to the next layer, right? So this is one of those transformations. WF is doing one such transformation. But before doing that transformation, you first do this mixing on the bigram level and then do the transformation, which does not happen in transformers.
But that mixing already happened before, right?
Yeah.
That's another level of mixing.
Yeah, but the purpose is different. Over there, the purpose was to create those gates which will do the exponential decay and the update. Over here, the purpose is to do some sort of a final output of that layer. What should be the final output of that layer? Yeah, before it goes to the next layer.
And mix of these are vectors, right? Not
Yeah, and I'll tell you why probably they have done this again, because they are constantly in this sort of a thing that you are working as a bigram. So at the first level you did that mixing, but then you will get this yt and yt minus 1. Now they cannot be living in a separate zone. They have to be again brought together into one common representation. So you're looking at it in that way, because if you don't bring this together, then if you can't unfold mathematically and get all the prior yt's.
But T doesn't have access to T plus 1. Are you talking about operators in per case or like the real encoder only?
Right now this is just encoding that is going on.
But T doesn't have access to T plus 1, right? You know, T is a mix of T and T minus 1.
Yeah, t only looks backwards.
Why is this so?
I mean, because it's more, if you look at it like a language model, you are always going to predict what's the condition so far. It is finally, because at the end of the day, if you look at the final head, the head of the Raku, that's the final layer. At the final layer, you will put that head which will do the autoregression, right? So that is the same. That is exactly the same as what would happen to any model, including transformers. So now the other guy, you create yet another gate out of the other guy, right? Which is this guy, xtg, right? And put a sigmoid so that everything becomes a percentage. And then what do you do? What do you do is you apply that gate on a squashed version of that UT. So think of UT as ZT, where Z was the contextual embedding in transformers. So think of U as the transformers transformers Z, or that contextual embedding, right? And you are squashing it because think of it, why squashing? Because you're bringing it all into this between 0 and 1 sort of a hypersphere. The same reason why in neural feed-forward network you would squash your internal representations, right? So you do an activation function. So this squashing function is ReLU square function. So that's what this ReLU square function looks like. So max of UT and 0 whole squared, and then you apply the gate on top of it. You don't let it go just like that. In transformer, you would have let it gone just like that. You don't do it over here. You apply another gate on top of it, and then you create your final ZT. This ZT, this is again parallel in the same way, and this ZT, you again make sure that the original information stays. So you apply the residual y prime t from where ZT was born. So ZT was born out of that one y prime t. So you again apply the y prime t so that y prime t is not suppressed in the ZT representation. So you add that again and you get y prime prime t, and that y prime prime t for a particular layer becomes the xt for the next layer, the input for the next layer. And it keeps going on, and then finally in the final layer you would do exactly what you would do, add a decision function if it is an autoregression, or if it is a masked language model, also you can create a masked language model out of it, or a classification header, whatever that you would want to do. So you from X you do time mix. After time mixing you do the WKV operation, you get y prime, you then do channel mixing, which is the analogy to the FFN in between, and you get Z. From Z you add the residual back, so there are two residuals, just like transformers. You get y prime prime, which is basically y prime, which is basically the residualized version of y prime, or rather, sorry, z. So stack multiple Rakov blocks and then LM head on top. Hmm? At this level, yeah. And before that, there was another one, right? So before before you started with the final, before sending it into your so-called FFN, which is this thing, you actually do yet another residual and then you send it. That part is pretty similar to transformers. Okay, so yeah, so far any question? So the interesting thing is that the original paper doesn't talk really about any multi-head sort of a learning. It's a bit difficult if you look at the paper. It's a bit difficult. I mean, that was one of the major comment also given to them in findings EMNLP. So it got into findings because one of the major comment was very hard to process because the way it was written.
There is no reason to believe that its expressivity is better than transformer. I don't find it convincing to believe that its expressivity would be better than transformer expressivity.
I look at it like more from an experiment. I look at it more from an experiment point of view that, okay, you have doubt, you think that there is a exponential decay component that needs to be added explicitly. Let's find it out. I look at it more like that. Let's find it out and see, whether that really is the case or not.
Yeah, but this assumption may not be true, right? For example, in case of long range dependency, right? If you think of exponential decay, right?
Yeah, I think it's a bit troubling. It's a bit troubling.
Exactly.
I mean, it may work for, let's say, weather and those sort of data, weather data or other kind of data where exponential decay makes sense.
But also, let's say, application like people in the healthcare kind of problems where you have some answer hidden inside the long context, right? And let's say the answer appears at the beginning of the context.
Right,
You
right,
will
right.
never be able to retrieve that answer.
No, I'll tell you. The there is a result.
Oh, there's a result.
There is a result which, if whatever I could gather at least, that that so the ARC, the typical ARC challenge, the AI2 reasoning challenge, right? So what it does is it has multiple choice science questions. You guys know? Have you seen this benchmark before in some other previous lectures, or am I repeating it? Okay, so basically it's a multiple choice science question, just like your MCQ kind of question papers, and it requires factual recall and some amount of reasoning. So general logical reasoning over knowledge. So that's what it takes, right? Test. So what it did was it looked at so as you what it tried they try to see whether the accuracy improves as they improve the training regime, as they increases the training regime, right? In terms of the exaflops or the compute. By exaflop, what we mean is, so one flop is one floating point operation, which is one single arithmetic step. So the compute would mean the model size multiplied by the dataset size multiplied by the number of training steps, right? In terms of epochs and all. So as the training steps increased, of course, we can see that Rakov is beating OPT and Pythia and Bloom, with which they can somebody help me in tracking the time?
So 1 hour plus, already done with this.
Down by?
It's 1 hour plus.
I'm already, okay, 15 minutes हो गया. So do we complete that on Monday, or
You can wrap up the question, maybe
this one?
yeah,
Okay. No, I have some more evaluation. So
more evaluation.
yeah. So maybe I can finish this and I can, yeah. So, so an interesting thing that the way to understand such plots is you need to understand that with the same regime, or compute, are you able to get better results than previous one than other models or not, right? So let's say that 30 accuracy 30. Am I able to reach? When am I able to reach accuracy 30? So that's somewhere around 10 raised 3. Now, if somebody is able to do that before that, let's see, then that model is a better model because it's able to reach that amount of accuracy at an earlier time with less compute, which is a good thing to do. What these guys are trying to say is that we are able to not only beat, but in many of these cases, we are able to achieve higher accuracy in less compute. Right, so that's what they are trying to claim. Although yes, so if you look at only, these were a bit older models, those are all transformer based models, Pythia and Bloom and OPT, bit older models, but of the same size as what Rakov models, this particular model is, right? Swag, again, it is very comparable to the best ones. Swag is basically you have to pick the most plausible continuation of a short story. So it measures common sense reasoning and event plausibility, right, in terms of perplexity and all. So again, you see that the accuracy is better. Lambada from OpenAI, again, predict the final word of a passage given full preceding. So this actually, tests your long context range sensitivity, right? And again, it does pretty good, provided you give it more compute, and it is comparable to these models. OpenBook QA, small science reasoning tasks. They did that. I did not put it on my slide, but if you go to the paper in the appendix, right below in the appendix, they have a lot of other challenges which they looked into. So this is reading comprehension with common sense reasoning. So basically, closed style question answering. Fill in the blank. We'll look into this long range arena. This is where things get a bit interesting on Monday, and then we will go into state space machines. We can think of state space machines and the modern versions as like a subsequence of Raku style models. Although it got a lot of traction in terms of, because it's still you will see, including NeurIPS and ICLR and all, there are a lot of models in visuals and visual domain and image processing domain which are taking Raku as an inspiration based model and then building on top of it. And even today, this Rakov is no more the Rakov, because if you look at Rakov, I think Rakov 7 or something like that has come up. So these guys are building this their goal is to challenge the transformer based models and to see if they can beat or be as good as the transformer based models with lot less compute, like real compute, not big O complexity level, but real compute.